talking about dimensional analysis. Dimensional analysis is an organizational tool that can be used for converting from one unit of measurement to another. In our first example problem, we know that Mr. Sutton can throw a fastball at 44.5 miles per hour. And we want to know what this is in meters per second. So our given piece of information is the 44.5 miles, and the per tells us that hours go in the denominator. We want to know ultimately what this value is in units of meters per second. So we're actually going to have to go through two unit conversions, one going from miles to meters, so approaching the distance, and the other converting time from units of hours to units of seconds. We use something called a monorail to track our units in chemistry, and so I'm going to go through and show you how this process works. The first thing I want to talk about, though, is the conversion factor here that we're given. In dimensional analysis, we use conversion factors, which are equivalent statements, telling us that, in this example, 1 mile equals exactly 1,609.344 meters. We can take this conversion factor and we can express it as a fraction. We'll start with one that you're a little bit more familiar with. Let's say that I had 3,215 feet and I wanted to know how many miles that was equal to. I would need to know a conversion factor in going from miles to feet. We know that 1 mile is equal to 5,280 feet. So we could use this value here as our conversion factor to go from miles to feet, or feet to miles. Now, when I look at this conversion factor, I can express this as a fraction. I could write it as 1 mile over 5,280 feet, or I could also express it as 5,280 feet per 1 mile. These values are equivalent to one another. So now we'll go ahead and look at the conversion factor that applies to our problem here. If we have 44.5 miles per hour as our given, and we want to get to meters per second, we first need to find a unit that is going to allow us to go from miles into meters. That's our first unit conversion. So here I have 1 mile is equal to 1,609.344 meters. I can express that as a fraction, and I want the fraction to be written so that miles is on the bottom, so that it will cancel out. So I'm going to put units of miles on the bottom, units of meters on the top. And I'm going to use this conversion factor here in order to do this mathematically. So I'm going to take 1 mile and set it equal to 1,609.344 meters. Now, if I stopped right here, I have miles on the top and miles on the bottom that would cancel out, and I would be left in units of meters per hour, which is not a very useful unit in terms of measuring the velocity of a baseball or a softball. So now what I need to do is my second conversion, going from meters per hour into meters per second. The unit that I'm trying to get rid of is this hours here on the bottom. Since I have hours in the denominator, if I want to get rid of this, I need hours, the same unit, in the numerator. So what I'm really interested in is a unit conversion factor that takes me from hours to seconds. So we want to think, how many seconds are in an hour? We know that there are 3,600 seconds in 1 hour, and as such, we can go through and we can convert into meters per second. So we want to take a look at all of our units and make sure that they're all going to cancel out. I've got miles on top and miles on the bottom. Meters on top, there's nothing to cancel with meters, so I'm going to leave that. And then I have hours on top and hours on the bottom. So we're going to be left in units of meters per second, which is what we want. In order to do this problem, we're going to go ahead and type this into our calculator. We want to take all of the values in the numerator and we're going to multiply them across the top. And then we're going to divide by what we have in the numerator, or I'm sorry, the denominator, excuse me, so 3,600. When we go ahead and do that in our calculator, we get 19.9 meters per second. So this is our final answer. Now, this next problem here gets a little bit more complicated. It moves beyond just simply converting from one unit of measurement to another. In this next problem, what we're going to do is we're going to see how dimensional analysis can be useful in the world of chemistry. How we can actually solve for one variable by taking a given and converting from one unit of measurement to another. So let's go ahead and take a look at this problem. The Saturn V rocket used to launch missions during the Apollo space program made use of a mixture of liquid oxygen and highly refined kerosene fuel as its propellant. The density of kerosene is approximately 0.78 grams per cubic centimeter. The combustion of kerosene results in the release of 46.2 megajoules per kilogram of fuel burned. The first stage fuel tank of the Saturn V rocket holds 203,400 gallons of kerosene fuel. How much energy is released during the complete combustion of the fuel in the first stage tank? So there's a lot going on in this problem here. The first thing that we want to really look at is figure out what is it that we're actually trying to find. So ultimately, we want to know how much energy is released. We want to be thinking, what units do we use in chemistry for energy? And we know that one of the primary units that we use in chemistry is the units of the joule. Okay? And here we have megajoules. So we are going to try to find how many megajoules of energy is released. So I know at least where I'm trying to go. The other thing that I want to look at is what my starting point is. So I'm looking to find my given. While we're given several different variables, our only given to start with here is the amount of kerosene fuel that we have in the first stage fuel tank. So we're going to start with the 203,400 gallons of kerosene fuel. And I'm going to abbreviate gallons here. So ultimately, we want to go from gallons of fuel into megajoules of energy released from that fuel as the energy is converted from the chemical potential energy into heat energy. In order to do this problem, there are several ways to approach it, but I think it's always helpful to look at what conversion factors you're given and to kind of map out where you want to go in terms of your units. I'm going to work backwards. I know that I want to find how many megajoules of energy are released, and so I'm going to look and see what information I have that relates to energy. So if we go up and we scan our problem, we see that the only thing that gives us units of energy here is this 46.2 megajoules per kilogram of fuel burned. So I know that the last thing that I'm going to be using is I'm going to be going from the megajoules per kilogram to megajoules of energy. Now if I backtrack from that, I want to find some variable that uses mass in it. So I look at this and I see, well, I've got the megajoules per kilogram value that I'm going to use. If I want to go backwards from that, I need some value that has kilograms in it. Scanning my other variables, there's nothing specific that has kilograms in it, but I do have a density, which is in units of mass per centimeter cubed. We know from our understanding of the metric system how to go from kilograms to grams, so I can work backwards that way. And then once I'm in units of grams, I know that I can go from grams to centimeters cubed using my density value. From centimeters cubed, if I take a look at some of the other values that I've given, I see that I have 1 centimeter cubed is equal to 1 milliliter. So I can go from centimeters cubed to milliliters. And then if I take a look at other conversion factors, I know again I'm going to need to use the metric system to go from milliliters to liters. And finally, I can use this conversion factor given that allows me to go from liters to gallons. So here what we did is we just retraced our steps going backwards. So if we reverse that, what we're going to be doing is essentially starting with gallons and going from gallons to liters, and then from liters to milliliters, from milliliters to centimeters cubed to grams, grams to kilograms, and kilograms to megajoules, where we will eventually get our amount of energy. So let's go ahead and put this all out in a monomer. Starting with my given, which is a value in gallons. We are going to take the conversion factor that relates gallons to liters, and if I start with a value in gallons, in order to get rid of gallons, I need to have that same unit in my denominator. When I have the same unit on top as on the bottom, those units cancel out. So I know that 1 gallon is equals 3.7854 liters. Now we're in units of liters. We want to go from units of liters to milliliters. So in order to go from liters to milliliters, I need to put liters on the bottom and milliliters on the top. From our knowledge of the metric system, we know that there are 1,000 milliliters in 1 liter. Next step that we're going to do is we're going to go from milliliters to centimeters cubed here. I'm going to tighten things up a little bit so I can fit this all on one line, hopefully. So I know that 1 milliliter equals 1 centimeter cubed. And then from here, we're going to go from centimeters cubed to grams. The value that I use to go from centimeters cubed to grams is the density of the kerosene fuel. The density of the kerosene fuel, if we go ahead and scroll back up here, is given to us is 0.78 grams per cubic centimeter. So if I have centimeters cubed on the top, I need to have centimeters cubed on the bottom and the 0.78 grams on the top. Now in our next step, we need to go from grams to kilograms. So in order to go from grams to kilograms, I'm going to make a little bit of room here and erase this part. And we are going to put grams on the bottom, kilograms on the top. That's what we desire to get to. We know that there are 1,000 grams in 1 kilogram. And then lastly here is where we use our value of megajoules per kilogram. So if I have kilograms on the top, kilograms goes on the bottom, and I have 46.2 megajoules per kilogram. Let's take a moment to calculate this. Again, everything in the numerator is going to get multiplied. So I'm going to multiply it all the way across the top, and then I'm going to divide it by anything other than 1 in the denominator. So this is all 1 here, so I'm just going to divide it by 1,000. Give us a minute to do that, and we end up with 2.8 times 10 to the 7 megajoules of energy. So this is the amount of energy released by the combustion of kerosene fuel.